So I thought I'd do one more example in this section in 5.1. I watched a basketball game and it's halftime, so I figured might as well make one more example. Maybe it'll help students to have one last example where my focus is more on doing a problem, maybe the hardest problem I can come up with, and less on teaching you how to do it, more just demonstrating doing it. So here's the question that I came up with as something that would be as hard as anything that you could see in this section. Estimate the area under this curve, f of x equals cosine of 2x, between negative pi over 6 and positive pi over 4, so those are my values of a and b respectively, by calculating R5. And maybe you walk into this problem with these formulas either memorized or understood well enough that you can use them, everything inside this box. And then I wrote a unit circle down here. Don't worry too much about that, but since I'm dealing with trig functions here, I'll need to know some values off my unit circle. And if you have those memorized, great. And if you don't, again, don't worry about it too much right now. Just reminding you of stuff. So how to get started? Well, it asks me to calculate R5. And if I have this formula for Rn memorized, I can write this formula for R5. What this is saying is to calculate R5, I'm going to have to add up 5 things. The area of 5 different rectangles. And each of those rectangles areas, I need to know the length of the base of the rectangle as well as the height of the rectangle. And since I'm using right endpoints, the height of the rectangles will correspond with x1, x2, x3, x4, and x5, which is why my index goes from 1 up to 5 here. In order to use this formula, I'm going to need to know what delta x is, and maybe also have some information on xi. So maybe up top here, I'll figure those things out. Delta x, as I have written over here, is always b minus a over n. So in this problem, it looks like a is given to me to be negative pi over 6, right here. And b is given to me to be pi over 4, down here. And n is given to me to be equal to 5. So I can plug those all into my formula for delta x and get that delta x is pi over 4 minus negative pi over 6. Sure, I'll write that. All divided by 5. Which is kind of a mess, but let's see. If I'm subtracting a negative, that's the same as adding. So I got pi over 4 plus pi over 6. And if I wanted a common denominator up there, I could think about the pi over 4 as 3 pi over 12. And I could think about the pi over 6 as 2 pi over 12. And that whole thing is divided by 5. And by thinking about it this way, I can say 3 pi over 12 and 2 pi over 12 gives me 5 pi over 12. And since that whole thing is divided by 5, I'm going to rewrite that 5 as 5 over 1. So that now I have a fraction divided by a fraction, because there's this handy little trick when you're dividing fractions, and it's changing division into multiplication by multiplying by the reciprocal of the denominator. In other words, just take the fractions down on the bottom and flip it upside down and change it into multiplication, which is really handy because now this 5 and this 5 cancel out, and I'm left with just pi over 12 as my value for delta x. So delta x is pi over 12. As I write out this formula, I'm going to need to know a lot of values of xi. My I is going to go from 1 up to 5. So I'm going to need to know what is, I don't know, over here maybe, x1, x2, x3, x4, and x5. All of these will be used in my formula. I think it helps to figure out x naught also, even though that one won't actually be used in my formula. It'll help me predict the rest of these values. And the reason I do that is because x naught is always just equal to a. X naught is always just this value of a, so in this case, it's negative pi over 6. And what I'm going to do to figure out the rest of these values is I'm just going to add delta x over and over again to the preceding value to get the next value. So what I'm saying here is to figure out x1, all I have to do is start with x naught and add one of these delta x's. Start with x naught and add one of these delta x's. Because these are fractions, these are kind of annoying to deal with. A nice little trick that'll help is, wait, I'm just going to be adding pi over 12 each time? Why don't I keep the denominators all in terms of 12s? Instead of thinking about this as negative pi over 6, why don't I think about it as negative 2 pi over 12? Because then it's super easy to add pi over 12s. Right? If you add pi over 12 to negative 2 pi over 12, you get negative 1 pi over 12. If you add pi over 12 again to negative pi over 12, now you're at 0. You add pi over 12 again, now you're at positive pi over 12. You add pi over 12 again, and now you're up at 2 pi over 12, which you might later recognize as just pi over 6. You add pi over just 12 to this thing one more time, and you get 3 pi over 12, which, again, you might recognize later is pi over 4 if you do some simplifications. So these are my various values for xi that I'll use in my formula, x1, x2, x3, x4, and x5. Maybe it's a good time to expand this thing. I want to add together 5 copies with the I going from 1 up to 5 of this expression. So I want delta x f of x1 plus delta x f of x2, and so on until I get up to delta x f of x5. Here is a good point for me to give you a little tip. You might notice that there's a delta x in each of these terms, right? There's going to be a delta x in every single term, and that's never changing that delta x because there's no i's here. Only the i's are the things that change. What that means is you can always just factor out a delta x if you want. There's a delta x in each of these things that I'm adding up. You can pull it out in front if you want and rewrite this formula so that it looks like this. That little algebraic technique is especially handy when either your delta x is kind of ugly to deal with, so you don't want to multiply it 5 different times into each of the terms, or when you have a lot of terms here, because again, it's kind of a pain to multiply it into each of the different terms. In fact, this is such a handy formula that some people write the formula for R5 as delta x times the sum from I equals 1 to 5 of f of xi. Right? These two formulas are equivalent. And this one, I'd argue, is a little bit easier to use algebraically. But I don't write this formula because I think this one has some nice intuition to it. This one, it just feels like a memorized kind of thing. But this one, oh yeah, I'm adding up 5 different rectangles. Rectangles, I'm thinking base times the height. Here's the base, and there's the height. You can use whichever formula you want. I just will use this one because I think it adds intuition for the student. At any rate, now that I've gotten this far, I can plug x1, x2, x3, x4, and x5, values I have listed over here, into my function, f of x, which is cosine of 2x. So R5 will be equal to delta x, which again is pi over 12, we calculated that earlier, times f of x is cosine of 2x. So I want the cosine of 2 times whatever x1 is. Well, x1 is negative pi over 12. If you multiply this by 2, you get negative 2 pi over 12. In other words, negative pi over 6. Do the next term for you, f of x2. x2 is 0. So what I want to do is take 0 and plug it into this formula. I get the cosine of 2 times 0. I just get the cosine of 0. Continue like that for your remaining terms. And you have a sum that you're ready to evaluate. And in order to evaluate this term, you have to have your unit circle memorized, which is why I wrote this up here. I just wrote the values of the first quadrant of the unit circle, because if you have those memorized, you can fill out the rest of the unit circle. As a reminder, on your unit circle, the x values are always the cosine values. And when I talk about when I talk about the angle here, I'm measuring it clockwise. So if I have a negative value like negative pi over 6, I'd measure it counterclockwise. Negative pi over 6, we'll be talking about this point right here, which I don't have labeled on my unit circle, but the x value here is the exact same as the x value here, which is root 3 over 2. What I'm saying is the cosine of negative pi over 6 is root 3 over 2. The cosine of 0, here's 0 right here. The x value at this point is just 1, is listed right there. Cosine of pi over 6 is this point. The x value is root 3 over 2. Cosine of pi over 3 is talking about this point way up here, and its x value is 1/2. And finally, the cosine of pi over 2 is talking about this point right here, whose x value is 0. 1, 2, 3, 4, 5 terms. Really, these are the heights of my 5 different rectangles, and each one individually needs to get multiplied by the length of the base of those rectangles. But it's easier algebraically to add them up first and then multiply that whole sum by pi over 12 than it is to multiply each one individually by pi over 12. If it helps you to have a picture, here's your picture. Here's what's going on. Here's the graph of cosine of 2x. My value of a is negative pi over 6, and my value of b is pi over 4. So I'm going from here all the way over here. I'm estimating the area underneath this red curve from this point all the way over to here. And my delta x is pi over 12. So my first rectangle goes exactly from here to here. So here's the base of my first rectangle. What should height be? Well, I'm using right endpoints, so its height is going to be based on this point right here. What's the height of this point right here? It's root 3 over 2. Why? Because I'm taking negative pi over 12 and I'm putting it into this function, cosine of 2x. So the cosine of twice this value is the cosine of negative pi over 6. That's why it starts out up here. My second rectangle will go between negative pi over 2 and 0, and its height will be way up here at 1, the right endpoint. My third rectangle will look something like this. My fourth rectangle will look something like this. And my fifth rectangle, interestingly, will go from here to here, but its height will be based on this point, which has a height of 0. So my fifth rectangle shouldn't have any height associated with it at all. Oh, that's where this 0 is coming in right here. All that's left to do now is add up all these values and multiply by pi over 12. If you want a decimal approximation, you feel free to do that. I prefer to deal with exact values, so I'm going to do that instead. This is 2 halves, so I got 3 halves, and 2 of these root 3's. So maybe I could say I have pi over 12 times 2 of these root 3's plus 3, all divided by 2, because 1 1/2 is the same as 3 halves. And then I could take this pi over 12 and multiply that through and call the entire thing, I don't know, 2 root 3 plus 3 divided by 24 pi. I call that my answer, this whole number times pi over. But at this point, it doesn't matter if you want a decimal approximation or exact approximation. Really, I'd argue that, I don't know, way up here you were done. I don't really need you adding numbers together and multiplying. I believe that you can do all that stuff. What I want you to understand is how to come up with this expression in the first place. And that's about as hard as I can make one of these examples.